Good morning. Today we will see bending stresses in beams. So in earlier classes we have learned how to determine the shear force and bending moment values and how to plot shear force and bending moment diagrams for different loadings and support conditions. So whenever external loads are acting on a beam, we know that the shear force and bending moments are set up at all the sections of the beam, which means that it is understood that shear force and bending moment, because of this shear force and bending moment, the beam undergoes certain deformation. So the material of the beam will offer some resistance to the external loading or some stresses against these deformations. The stresses induced by bending moment are known as bending stresses. Now let us see what you mean by pure bending or simple bending. So let us take a beam which is a overhanging beam of equal length on either side of the support. So you can see on either end a point load of W is acting. If I try to plot the shear force diagram, so this is my shear force diagram. So you could observe that for a portion of the beam of length L, that is between A and B, the shear force is zero or there is no shear force. Look at the bending moment diagram. I have got a constant bending moment value for a portion of a beam of length L between A and B. So, for a portion of a beam AB of length L, where there is no shear force or zero shear force, but subjected to constant bending moment, is nothing but the beam is said to be in pure bending or simple bending. So this is the meaning of what is pure bending or simple bending means a beam, a portion of a beam for which there is no shear force or zero shear force, but it is subjected to a constant bending moment. So the beam AB is said to be in pure bending or simple bending. Assumptions. Now I told you that bending stresses are due to bending moments and the shearing stresses are due to shear force. So now how to derive the expression for the bending stress. So let us see the derivation now. Before getting into the derivation, we need to follow some assumptions. Based on the assumptions only, we are going to derive the expression for bending stress. The foremost and very important assumption in most of the courses, in structure related courses, the material of the beam is homogeneous and isotropic. Homogeneous material is of same kind throughout, and isotropic means elastic properties are equal in all the directions. The value of X modulus is same in tension and compression. The transverse sections which were plane before bending remain plane after bending. The beam is initially straight and all longitudinal filaments bend into circular arcs with a common center of curvature. The radius of curvature is large compared with the cross-sectional dimensions. Each layer of the beam is free to expand or contract independently of the layer above or below it. I'll just explain all this with the help of a small sketch. So let me take for example, this is my beam, right? This is my beam. Okay. So we have the support here. Have the support here. Okay. So now for example, here for example, if you make a cut, okay. So if you look at from the side view, so I'll get like, if it is a rectangle section, so I'll get a rectangular shape. So this, I can call this as a transverse planes. So when the beam is loaded, so this transverse sections remain plane before and after bending. That's very, very important. Before and after bending. So once when the beam is loaded, the beam will bend. The beam will bend into a circular arc like this. It will try to bend into a circular arc. Circular arc means definitely it must have a center point and the radius r. Let r be the radius of curvature. So this radius of curvature is large when compared to the cross-sectional dimension. Suppose if the cross-section is a rectangle having width b and depth d, the radius of curvature will be large when compared to the width and depth of the cross-section. So before loading it is straight. When it is loaded, the beam bends into circular arcs. Okay, so circular arcs. So you can see, call it as a filaments. So here I'm having one filament or a layer, whatever it is, like this. So each layer is free to expand in the sense, if you look at the bottom surface, it is getting elongated, which is nothing but under tension. If you look at the top surface, it is subject to compression, it is contracting. So contraction happens on the top surface and elongation happens on the bottom surface. So each layer of the beam is free to expand or contract independently of the layer above or below it. If you look at this middle one, if you look at the middle one, for example, so this one, middle one, I call it as a neutral layer. I call it as a neutral layer, a neutral layer or a neutral plane, which doesn't undergo any tension or compression, which means that no deformation occurs. Okay, so we are going to follow that assumption also here. Okay, so now expression for this bending stress. So I've taken a portion of a beam. Okay, I've taken a portion of the beam. So I'm considering a small length of dx, a small length of dx. We're considering small elemental strip EF at a distance y from the longitudinal axis or from the neutral layer or from the neutral plane, whatever it is. Okay, this is the front view of the beam. So when it is subjected, suppose for example, when the moment is acting like this, suppose if the moment is acting like this, so here the moment is acting, so here the moment is acting. Okay, if it is subjected to external loading, moment M and M, for example, the beam will bend like this. Okay, this is before loading, this is after loading. So the beam bends into a circular arc. The beam bends into a circular arc where R is the radius of curvature and theta is the angle subtended. Okay, this is the portion we have considered here, and this is the strip. Okay, so this is called as a neutral layer, called as a neutral layer. And if you look at the from the figure, NN is equal to EF, which is nothing but dx or delta x. Some textbooks it is given as a delta x. Okay, so I'm taking as a dx. So N dash N dash is equal to NN, which is equal to EF, which is equal to dx. So I told you already it's a neutral layer. Okay, neutral layer or a neutral plane where there is no deformation occurs, so that length remains the same, that length remains the same, almost flat. Okay, not exactly arc, almost flat. Okay, so EF, this EF will increase to E dash F dash, which undergoes tension, and AC will decrease to A dash C dash, which experiences compressive force. Now n dash, this is now if you just imagine this a kind of a arc, for example, small arc, very very small arc. So how will you find the arc length, radius into theta? So r into theta, right? R into theta, n dash is equal to. And if you look at this e dash f dash, r plus y into theta, r plus y into theta. Okay. So this n dash is equal to nn. Okay. So nn is equal to b ef, which is equal to dx. Okay, so dx is the condition or the length we have taken before loading, right? So increase in length, so this is the after loading, e dash f dash, and ef is nothing but before loading, actually length. So ef is equal to nn or n dash is equal to dx, which is nothing but r theta. So you can write like this: r plus y into theta minus r theta is equal to y theta. So increase in length. Strain, only find change in length by original length. So here in this case, increase in length by original length. So increase in length is y theta, by original length is r theta. Okay, because r theta remains the same. N dash is equal to n is equal to dx. Y by r. So strain in the layer EF is nothing but y by r. How will you find stress? So stress by strain is equal to Young's modulus. Stress by strain is equal to Young's modulus. So here strain is given. Okay, stress, let sigma be the stress in that small element. Okay, so stress by strain is equal to Young's modulus. We can write like this. So now stress can be written as E into Y by R, E into Y by R. Now, if E, Young's modulus or radius of curvature is constant for a beam, stress, bending stress is proportional to Y. Y is nothing but distance from the neutral layer to the outermost layer or to any other layer below or above the neutral axis or neutral plane. So if E and I are constant, stress in any layer is directly proportional to the distance of the layer from the neutral layer or neutral plane, whatever it is. So what will happen? So here y is 0. So here the stress is 0. So as sigma is proportional to y power is 1. So the variation of the bending stress is linear. You could see the linear line. Okay, linear line. So top surface of the beam experiences compression. So the bending stress is compressive in nature. So this is the magnitude of the stress. Nature is compression. At the bottom it experiences tension or tensile. So this is a tensile in nature. Bending stress tensile in nature at the bottom of the beam. So here it is 0. So this is the magnitude. So the variation of the bending stress across the depth of the beam is a linear because y power is 1. So in turn we can write sigma by y is equal to E by R. Sigma by y is equal to E by R. Okay. So as I told you, the variation of the stress is linear. This is across the depth of the section. Okay. So if you look at the side view of this beam, it would be a kind of a rectangular section. I told you already. If you look at the side view, it is a rectangle. Okay, like this. Okay, rectangle. Side view will be rectangle because we are taking a rectangular section for our explanation. So rectangle section I've taken. So I told you in the front view if you look at, so I call this as a neutral layer or a neutral plane, neutral layer or neutral plane. When you look at the side view, I call it as a neutral axis. Okay, neutral axis. So at the neutral axis, bending stress is 0. This we need to keep in our mind always. At the neutral axis, bending stress is always 0. So let us consider a small strip, okay, of thickness dy at a distance y from the neutral axis. Okay, so we have calculated the stress. Okay, let dA, small letter dA, capital letter A, dA be the elemental area. Okay, elemental area. Stress already we have calculated. Stress sigma is equal to E by R or E into Y by R. All you calculate the force stress into area. Okay, stress into area. So now we got the force on the layer. How will you calculate the moment for this? Moment is nothing but force into distance. So this is the force acting on this small strip. This force into y. You'll get y squared by r. E into y squared by r into dA. So this is the moment of resistance offered by the strip about the neutral axis. About the neutral axis. Okay, this is nothing but the moment of resistance offered by the material of the beam, which is nothing but internal resistance to the external loading or externally applied bending moment. Now to find the total moment of resistance about the neutral axis, you just integrate it. Integration E y square by r into dA. So I can take E by r outside. Integration y square dA is nothing but area moment of inertia. Area moment of inertia from engineering mechanics. Okay, integration y square dA is nothing but area moment of inertia, which is represented by the capital letter I. So I can write like this. So this is the resistance offered by the metal of the beam. So this moment of resistance must be equal to the externally applied, equal to the moment produced due to the externally applied loadings. So let that moment be M, for example. Let M be the external moment applied of the beam or the moment due to the externally applied loads. Very, very important. So both should be equal for equilibrium. So M is equal to E by R into Y. E by R into Y. So M by I is equal to E by R. So we know that E by R already sigma by y. So we can write m by I is equal to sigma by y is equal to E by R. So here to avoid confusion, I'm going to use in future sigma as sigma b, sigma suffix b, which is nothing but the bending stress, okay. So m by I is equal to sigma b by y is equal to E by R, where m is the maximum bending moment for the given loadings. I is the area moment of inertia. Okay, so I will be here, for example, if I take a beam, suppose this is my beam, okay. Suppose it is load is acting, for example, W, or this is my support, and this is my support. If you take the cross section is like this. Suppose if this is my x-axis, B is the width, and D is the depth. So I will be BDQ by 12. Y will be D by 2, total depth divided by 2. For asymmetric sections I'm talking about, okay. So I is nothing but BDQ by 12, Y is nothing but D by 2. So what is the radius of curvature? That will be given in the problem. And sigma B is the maximum bending stress and E is the Young's modulus. Now M, for example, we have seen most of the beams with the standard loading in the sense simply supported beam subject to the point load in the middle. What is M value? WL by 4. Simply supported beam subjected to an eccentric point load. What is M? WAB by L. Simply supported beam subjected to UDL throat. What is M? WL square by 8. Cantilever beam subjected to point load the tip. W, for example. W into L is the maximum bending moment. Cantilever beam subjected to UDL throughout the length. M is nothing but WL square by 2. Cantilever beam subjected to a couple at the free end. M is nothing but equal to couple. So these, for all these loadings, we know the formula directly. If you have a combination of loadings, now I have a beam where I have got a point load, UDL or UVL or a couple, whatever it is. So for the given loading, we have to determine the maximum value of bending moment. How to determine the value of maximum bending moment that we have seen already in shear force and bending moment topic? We need to locate where the shear force is zero. We studied already a point where the shear force is zero. That point corresponds to the maximum bending moment. So we need to write down the shear force expression at that location, equate to zero, determine the location of zero shear force. Then about the same point, we have to write down the bending moment expression. Substitute that x value, you will get the maximum bending moment. That maximum bending moment only we have to substitute in place of m as maximum bending moment, so that you will get the maximum bending stress. Thank you.